All right, so we go to friction rate. Actually, our step-by-step instructions is telling us to start drawing ducts. Let's go ahead and do that. That's actually more fun. We'll get to friction rate in just a minute. All right, so in the step-by-step instructions, we're on step K, duct draw mode, and that's actually changed. That's now HVAC draw. I need to update those. So it's HVAC draw, and it says place at least one register in every room, and then place one return grill, and then draw the ducts, okay? So we've already placed our furnace because we needed to do that in order to tell the software how many systems we have. So we've already got our furnace there, our air handler. So I'm going to scoot that over. Let's get it tucked up next to the attic access. I'm just looking straight down from above here. So here's our attic access. Let's say our, I just noticed something. I drew these vaulted ceilings in here, and just because I wanted to show them to you, and I left them in there, so now I got to deal with them. In the earlier example, I didn't have those, so I need to change something. So when your vaulted ceiling goes like this, your trusses are probably running left to right in this house. The roof trusses probably go up and then come down here. And so the space where I have to put this furnace probably runs front to back. So I need to rotate my furnace. There we go. And I'm going to put it right here. This is way bigger than what the furnace would really be, but it's easier for you guys to see. Okay. So I'm going to rotate the furnace. You have to consider what kind of space you have up in the roof, where your attic access is. So there'll be a little access platform here. So the service tech can climb up the attic access, sit on this platform, and service the furnace. So the service side of the furnace will be facing this direction. We have this free draw thing here where you can draw shapes and stuff. So you could actually draw your furnace platform there if you wanted to. All right, but I got to put some registers in here. All right, so click registers up here in equipment mode. And then similar to Windows, you just hold down the Alt key and then click where you want the register to go. By default, it will put in ceiling registers. If you want to put in floor registers, there's a button over here that says place on floor, okay? And you can actually go underneath the house like this, flip the house and look at the house from underneath, and you place registers from underneath if you want to. So you can do floor registers or you can do ceiling registers. By default, it does ceiling registers. We'll look straight down from above. So there's a ceiling register. You can change those sizes. It defaults to 12 by 6 by 4 inches tall. Okay, you can change it down here. And you can also do sidewall registers by just clicking on a wall. So in this vaulted ceiling, instead of putting registers in the ceiling, I'm going to put high sidewall registers in these knee walls. And I just hit Alt, click, and click. Okay. So see those registers are in the wall there. Okay. That's going to serve the kitchen and the living room. I put one in bed 1. I need to put one in bed 2. And I need to put one in the bathroom. Okay. Now, I have an article about register locations. It's kind of funny. One of the most contentious topics I've ever gotten into related to HVAC design was where in a room you should put a register. Some people will insist that the register needs to go over the window. Okay. And some people will insist that the register should go back inside the room, blowing across the room towards the window, okay? They all have advantages and disadvantages. Whichever one you do, you have to do it correctly. And by correctly, I mean you have to use the right kind of register, okay? Generally speaking, interior to the room, blowing across the room is usually more energy efficient because it's gonna have shorter ducts, okay? The other thing that's very important, and I talk about this in the article on my blog and also in the book HVAC 1.0, is mixing. You want to make sure the room has good mixing. My general rule of thumb for good mixing is to blow the air the opposite direction that it's going to go naturally. And by naturally, it means the air is going to want to go back to the return. So blow the air the opposite direction. So we've got this room with a door over here. And as the air comes in, it's going to want to go out the door to get back to the return. So blow it the opposite direction. So being interior to the room, blowing across the room will encourage better mixing. The air will come across, it'll lose velocity, it'll settle, it'll mix, and then it'll shoot out, or it'll be drawn out or push out the door, okay? As opposed to, if you were to put the register here and make this a two-way register, half of that air is going to go straight out the door, half the air is going to go to this side of the room, go around, and then come back out, and then you'll get a big stagnant area over here by the window. All right, so keep that kind of stuff in mind. Again, this is more of an advanced topic, so just to keep things simple and keep them out of the way, I'm going to go against my own advice. I'm going to put them sort of out this way. By the way, in Las Vegas, they insist, or at least back when I was doing design, that the register be a square, four-way register centered on the room. That's how they do it in Las Vegas, or at least back in the day. Okay, so I've got these high sidewall registers. I've got all the registers everywhere I need to go. 1, 2, 3, 4, 5. There's 5 rooms. Okay, the next thing to do is I need a return grill. So I'm going to put it in this little hallway here. So I'm just going to place a register. It's like a normal, sidewall register. It's like a normal register. And you can see the shadow is going to line up in the hallway there. I'm going to change the size just so that it looks like a return. Okay, give it a nice, good size. I'm going to rotate it there. So that's going to be a return. The whole thing about sizing registers and sizing grills, that's manual T for terminal selection. Let's see. All right, so that looks pretty good. Now I'm going to connect those registers, the supply registers to the supply side and the return registers to the return side. That's how the software knows the difference between a supply and return register or grill is which side of the furnace or air handler it's attached to, okay? So to attach a duct to a box, a plenum, we're going to use something called a start collar. They might be called something in other parts of the state. But it's basically you cut a hole in the box and you attach a collar and you attach duct to it. We're gonna do a flex duct design, okay? You can do sheet metal, you can do rectangular. I have a whole video on our YouTube channel about how to do that, but I'm gonna keep it simple here. And let's see, I'm gonna go to flex duct and you just highlight the start collar, highlight the register that you want it to go to, and you hit enter. And it draws a duct. Okay, we'll do that here. I'm going to do that here. I need a couple start collars, so let's go back to start collars. Pull in there, flex duct, there, enter, there, enter. Okay, I've got all but one of them. So I got this little bathroom here. And the question is, should I just run it straight off of here? Avoid the end of the plenum. Avoid attaching ducts out here on the end, because if you think about it, the air is screaming through this box into this other box, and all that air is kind of crashing into the end of this box. So the pressure hitting the end of this box is very high. So if you were to attach a duct to the end like this, that duct is going to get a lot more airflow than ducts coming off the side. So avoid that if you can, okay? So there's a couple ways to do it. You could just run a little duct off the side here. We know that duct's going to be pretty small. And the ducts that I'm drawing now are just a default size, and you can change the default. At some point, we're going to lay out the ducts, and we're going to hit a button that says auto size duct, and it's going to size all the ducts based on the airflow, okay? But right now, we're just doing kind of a basic layout. These ducts are all bigger than they probably need to be at this point. So we could put a little start collar down here and we can attach the duct.
Dove is saying if you can show me how to put on a tie on a start collar, a TY on a start collar if you have the time.
A TY straight off a start collar, or in the middle of a duct?
That's why. Oh, NCI encourages one. Oh yeah, he says yeah.
Okay.
One trunk off the top and branches from that on NCI.
Yep. Okay, so we could do it like this. Okay. But I want to show you a TY. So I'm not going to do, that would be very reasonable. It's a nice short run. That would make plenty of sense to do that. But I just want to show you what a TY looks like. And so what I'm going to do instead is I'm going to branch off of this other duct, this duct here. I'm going to branch off of here and run it over here. And to do that, you have to be in flex duct. You highlight this handle here, by the way, you can move everything. See these colored arrows? If you want to move up, grab the up arrow. If you want to move left and right, grab a left and right arrow. These green boxes here change the angle of attack where the duct is coming into something. So if I want it to be sharper, I can bring it down. If I want it to be more gradual, I can bring it up like that. And there's also one hiding back in here. So you can really change the shapes of these ducts like that. All right, so to create a TY, highlight that handle. Whatever's checked over here where it says new fitting type, it defaults to TY. So when you highlight that handle and you hit enter, it's going to turn into whatever it says over here. Okay, so I hit enter, and now it's a little TY. It's kind of big and bulky because that makes it easier to click. So flex duct, so I'm going to highlight this connector point here. I'm going to highlight the register, and I'm going to hit enter, and there's your flex duct. So that's a little TY right there. These handles go away if you click into a different mode, like Windows or something. The handles go away so you can kind of look at it. All right, so that's our basic layout. There's kind of this little knob in here. We can fix that. I'm just straightening it out a little bit. There we go. That's better. Okay. Now let's do our return. So we got this great big return grill over here, and we need to attach a duct off the back and bring it over to that return. There's a couple ways we can do it. Now remember, we've got this attic access. So the service tech has to come up this attic access and get on top of here, and there's going to be a bunch of stuff in the way. So let's clean that up a little bit. So the HVAC draw flex duct. Let's move this duct kind of out of the way a little bit. Give the technician a little bit more room. Now notice this 90-degree elbow in here. We're going to have to account for that in a minute. I'll show you how we do that. And then we also have to get a return to get over here. So we want to keep this area clean for the technician to come in through that attic access. So I'm actually going to attach the return duct to the top of the plenum right there, instead of doing it on the end over here. So I'm going to attach a duct from there, flex duct, there to there, hit enter, and there's a return. Now, it's kind of taking the shortest path, and remember, we need to keep that area clean, so I'm going to clean it up a little bit. I'm going to raise this up out of the way, kind of get it up close to the roof. We want it to touch the roof. Bring this up, bring it over. Maybe we can run it. Let's run it along, kind of run it along the top of the furnace like that. Now we're keeping it out of the way, a little high. Let's bring it down. It's a roof. Depends on where the peak of the roof is. The peak of the roof is up here coming down. We're going to need to bring this down quite a bit more. Okay. Anyways, you can play with that and kind of get it to look right. Okay. And let's make that return a little bit bigger. Let's make it a 16. Be a little bit more realistic. Okay. All right. So we've drawn a duct system. Let me turn off the handles. I'll look at it a little better. We've taken a first crack at our duct system. You notice these overlap a little bit. I can clean that up if I want to. Let's go back, HVAC draw, move these out of the way so they're not, those two ducts are overlapping each other there. Clean it up just a little bit. And there's a lot of different kinds of fittings you can do and all kinds of other stuff. You can watch some of the videos and it'll go through, splices and TYs and tri-Ys and pants-wise and all different kinds of fittings. Let's kind of remind me, let's show Dob what he wanted to see really quick. He wanted to see.
Oh yeah, so I think a TY coming off of
straight off. So how do I make a TY come right off of that? So I go here, I go TY, then I go fittings, or do I just hit enter?
No, you go to do a rigid round duct.
Oh, that's right. So what you have to imagine, Dob, is that there's a 1-inch round duct attached there. And then what, Connor, that
so just make sure the right one's selected and press enter.
Yep. Okay.
And then you can drag it down.
And then you just
go to
fittings.
And someone was asking, what did you hit to convert it?
Enter.
Dob.
Just enter. There you go. So what it is, it's rectangular round duct, but you're just basically making it 1 inch long. And then you go back to flex ducts, and you can attach flex ducts to that TY coming off there. Okay. Okay. All right. So we got our basic layout. Now we're going to do friction rate. We'll go our step-by-step instructions, stuff around the friction rate. Okay. I don't have a good copy of the friction rate of the equivalent length table. Let me just kind of show you how easy it is to find stuff online when you need it like this. So I'm just going to go to Chrome, and I'm just going to type in the search bar ACA manual D equivalent length. Enter. And then go into the images, and there you go. Look at all those. So let's look at this one here. So these are different fittings. How to determine friction rate for residential duct design. HVAC school, hey, that's a good website. It's in the way. HVAC school, by the way, put in a plug for those guys.
Someone saying,
well, they can't see it.
Yeah.
My bad.
And then Robert Rise was asking, why do a home run for the 2 sidewall registers instead of a TY?
Because it's a really, really short run, and it's a start collar is cheaper than a TY. Plus, if you had a big duct going to a TY, that's another size duct you have to buy. So that might be a 10 going to 2/8. So then you have to buy a 10, you have to buy a TY. It's cheaper to buy 2 start collars and just have the 8-inch ducts come straight off. That comes from experience.
And the effective length.
And effective length is also part of it. So this is, if you look in Manual D, there's many pages of these equivalent lengths. And what they've done is they've quantified a pressure drop through different fittings by equating it to a length of duct. So instead of saying this fitting has a static pressure drop of 0.057, inches of water column, they say this fitting is the same as 20 feet of straight duct. So they just equate it to straight duct. And so if you look at all these interesting fittings, like this weird little side mount boot, this other kind of registered boot, these different kinds of grills, they all have these ELs, equivalent length 60, equivalent length 20. So the resistance to airflow of the air passing through this fitting right here is essentially the same as the pressure drop of the air traveling 20 feet down a straight duct. Okay, that's why they call them equivalent lengths. So it's just a nice handy way to make everything kind of speak the same language, and it makes the math a lot easier. Okay, so here's like a return grill down here. Here's some really weird floor boots. Look at this one. 100 feet equivalent length because the air has to come through here. It's basically going through one of these, which is 50, and then it's making a right-hand turn and coming up. So it's like this and this together. So it comes along 50, another 50, so that's 100 feet equivalent length. So that, all that stuff, what that does is it's taking from your static pressure. Remember how I said that 0.5 is like your bank account, and as you drive down the road, you lose money, you're losing pressure. And if you have to make these really sharp turns, you lose more pressure. So you have to account for these things. And what happens is if you have too many of these in here, at some point, your duct has to get bigger to compensate for that, okay? And so that's all what the equivalent length and the friction rate calculation is all about. All right, so again, I will put in a plug for HVAC School. It's a really good Facebook group too, by the way. If you're an HVAC technician, a lot of really tough, interesting questions get asked and answered on the Facebook group, HVAC School. All right. Let's see here. So we got all this stuff. I'm going to click on friction rate. Oh, the other thing that's interesting to understand, that's good to understand, is I can find it here. And again, I just found this online, and this was kind of cool. It's an ACA Manual D friction rate worksheet. If you open up Manual D and you find a friction rate worksheet, this is what it looks like. I'm gonna fit it to one page. Okay. So you've got this step one, which is your manufacturer's blower door, and this is kind of cool. This came from the town of Hanford, Virginia, had this posted on their website, like the building department or something like that. So someone made this, and you type in some numbers here, and you type in some numbers here, and I think it does the math for you if I typed in numbers. But so this is straight out of Manual D. We got this manufacturer's blower there. Here's our external static pressure. So that was our 0.5, and our CFM, that was our 601. And this automatically gets done in the software. I'm just kind of showing you where it comes from. Then you have these pressure losses. Then you have available static pressure. So you start with pressure, you lose some pressure. Then you have available static pressure. And then you have all your equivalent lengths. And then there's this formula. Available static pressure times 100 divided by total equivalent lengths. That's the formula for friction rate, okay? And then Manual D, let me zoom in here. Manual D has these recommendations for a maximum and minimum friction rate. And if you look at what's right in the middle, so the minimum is 0.06, the maximum is 0.18, okay? And if you look right in the middle is 0.1. And a lot of people say, oh, that's a rule of thumb or whatever. That's a good starting point. Okay, 0.1 is a good starting point, and then as sort of a target. If you know you're at 0.1, you're in between the Manual D maximum and minimum. So 0.1 is a good sort of target to shoot for, but it just depends on your actual system. How long are your ducts? How many fittings do you have? Because all those go into this equation, which is where this comes from.
That was asking, please zoom back a bit, or back in a bit.
Zoom in?
Yeah, please zoom back in a bit.
Like that, or am I going the wrong way?
Could you kindly repost the link to the PDF files? Yeah, is that under downloads? This particular one, I just Googled ACA Manual D friction rate worksheet, and this was one of the first ones that came up. There was tons of them in there. Okay, but here's the point: you don't need to do this. This is built into the software. This is built into Quick Model. I'm just kind of showing you when I start explaining Quick Model. I want you to realize that this is what's going on. Except what's not in Quick Model is this table here. What about the PDF from last night?
Which one? The floor plan?
No, you had like a step by step or something like that.
Oh, I put the link in if you scroll up in the chat to about 7 o'clock or so.
Sorry about that. I just didn't know where it was. Okay, I'll repost that.
Yeah, it's up in there. The step-by-step instructions, yeah. Okay, so this is just the guideline. 0.06 is as low as Manual D suggests. And again, this changes somewhat for variable speed furnaces too. And then 0.18 is as high as you want to get. If you're too low, it's saying inadequate fan performance, reduce your equivalent lengths. If it's too big, your fan's too powerful, decrease the speed, add some resistance, okay? But right in the middle is 0.1. So that's kind of where we're gonna kind of shoot for, is our 0.1 range. What time? We started at, we started at 6, so like 6:10 maybe. Okay, go back. So that friction rate table I just showed you should look familiar, because here is the step 1, step 2, and here's our available static pressure. Here's that equation, available static pressure times 100, and here is our friction rate. Now, 0.362 is really high. That's higher than the 0.18 we were shooting for, but we haven't done anything yet. Okay, so we have to put some numbers in here. So here is our 0.5 and our 601. Remember that from our manual S? This automatically is pulled from the manual S, where we entered 601 CFM at a static pressure of 0.5. And that is, let me pull this down here where you can see it. Just kind of show you where that sort of thing comes from. So here's that imaginary furnace. Here's the 0.5 inches of water column right there on high speed, and here's the CFM. Now this isn't the same furnace, but I'm just kind of showing you where it's coming from. There's our 0.5, and imagine that right there said 601. Okay, it says 1200 for this particular furnace, but that's the numbers that we put into the manual S. Those numbers are being pulled back into the tables here, 0.5, 601. Okay, and basically what we're saying is we need to move 601. We have 0.5 external static pressure to work with. We need to size our ducts to ensure that when that furnace turns on, it's not working at a static pressure more than 0.5. Okay. All right, I think it's a good time to take a break. It's 5 after, and let's take a 10-minute break.
Go to friction rate for this table to come up.
Oh, yeah, it's across the top. We're in the friction rate tab. It's 2 buttons to the left of the energy gauge tab across the top. Yep. All right, so let's take a quick break. Feel free to ask questions if you got questions, but we will reconvene at 8:15.
No
8:15. You still there, Steve? You're still on mute, Steve. Steve may have stepped away. Oh. You said music. with the,
Ben's asking, how do I get the fictitious USA furnace?
I just found that online. What you would actually do, that's going to be a real furnace manufacturer. So if you know a make and model number, and Eric was saying you can get those in the, yeah. So let's say you deal in Goodman equipment or Carrier equipment, and that it's gonna say Carrier furnace, you know, I forget the Carrier model numbers, but whatever the model number is, just Google that and look for PDFs. So you're going to want to see furnace specs, things like that. And here, let's just do it real quick. Oh, great. There's so much more accessible online today than there was when I was doing a lot of design. It's just, it just boggles my mind. So let me open up Chrome here. So that's it open. Open.
Yeah, you already got that window open. That's what you just selected.
Why can't it won't let me open my tray at the bottom.
Don't maximize it.
Okay.
Oh, it's a screen share thing, I think.
Yeah. I can't do it on this one because the way I have
Just press the Windows key. And type in Chrome.
Right here. All right, so I just opened up a Chrome window, and let's just say I'm just going to type in Goodman furnace specs. Here's all different kinds of furnaces over here. Like here's one, Goodman brand furnaces. Go to their website. Again, I'm not promoting anybody. I just, first thing that came to my mind. So let's go heating. Go furnaces. Actually, it's easier. So going through their website, it's easier to just find it direct. Just kind of look for PDFs. Here we go. Here's some model numbers here. If you know the model number, that's all you got to just type in. I just don't have any model numbers off the top of my head. There we go. And then usually on these pages there'll be like specs and stuff like that. There we go. So this is what you're looking for, something like this. So here's, and it's a PDF file. Notice it's 16 pages. So it's going to have right there, airflow data. That's what we're looking for. So every manufacturer shows it a little bit differently. They'll have, you know, one will have certain things down the row and certain things across a column, and another manufacturer will flip those, and another manufacturer will do it differently. But so let's go to page 7. Got all your dimensions and stuff. And CFM and temperature rise versus external static pressure. So here's our static pressure. There's the 0.5. Okay, notice it's usually kind of in the middle. And then here's your different models down the sides here. It shows your dip switches for your speed taps. And then here's your CFM. So their smallest furnace is this GMES 80040-3A, probably 40,000 BTU. At half-inch static pressure on high speed, it'll move 441. The next one up will move 458. The next one up will move 474. Oh, sorry, there's a speed tap. Oh, I'm doing it backwards. Sorry. It's going low to high. It's high is down at the bottom. That's different. I'm used to seeing it the other way around. So it'll at high speed, they don't show the speeds over here. They're showing the speed taps, but it should be obvious if I was paying attention. High's down here.
So 981 on high speed. I thought 441 was kind of low. So this furnace on high speed at a half-inch static pressure will move 981 CFM. At medium high speed, it'll be 759. So it's kind of bizarre they have it backwards like that. It's trying to be different. So this is where so these are the numbers, this half-inch and this CFM. And if you can go up to 0.6 and still get the CFM that you need, what that'll do is that 0.6 will make your friction rate different, which will allow you to put in a little bit smaller ducts, okay, and still get your CFM. Sometimes 0.5 can be a little challenging to meet. The other thing that I probably should grab here real quick too is your coil. Your indoor coil is going to have a certain static pressure drop as the air passes through it. And it's a pretty big chunk. It could be as much as half of your available static pressure, or of your total static pressure, your 0.5. And if that's the case, then you may want to bump it up to 0.6. But again, you got to make sure you're getting your CFM. So remember I said it's an iterative process. So I started off just taking some ballpark guesses, 400 CFM per ton at a certain static pressure. And then I'm going to lay the ducts out, I'm going to size them, and then I'm going to say, okay, now let's go look at some real equipment. And we might come here and say, oh, wow, this furnace gives us way more CFM than we need. We could actually run it, if we only need 601, we could actually run it on medium high speed and still get that. And we could run it at a higher static pressure. They just don't make a smaller furnace for some reason. So you may want to go, based on the size of this house, this furnace is probably way bigger than we need. So, and to be honest, that house is really, really small. You'll probably, a house that small, you're probably going to put a little ducted mini split in that house. The house as small as we're looking at, but you get the idea, okay? So we're just, this is where you get that information. If you look at Carrier, it'll be the same basic numbers. It'll just be organized differently. Okay, and so there you go. I remember back in the day, we used to have a guy come by, and these were all printed hard copy, and they fit in a 3-ring binder. And we had one for all of the 5 or 6 major manufacturers. And when I say 3-ring binder, this thing was a beast. It was like a 6-inch thick 3-ring binder. And it had all these pages and pages and pages of stuff. Now it's all online and it's all easy. You guys are so lucky. You're spoiled. All right. All right. About time to start back up. So for those of you who stepped down and came back, I was just showing an example of a real furnace spec sheet. And they're so easy to find these days. You just Google them basically. All right, let's go back, open up. Okay, so here's those two numbers, the external static pressure and our CFM, okay? And now we need to use those two numbers to calculate a friction rate, because a friction rate is how we're gonna size the ducts, okay? Airflow and friction rate and duct type give you duct size, okay? We're doing flex duct. If you remember in the libraries, there was a duct types. We have vinyl flex, sheet metal, duct board, and duct liner. And this roughness factor affects the size of the duct. Notice that vinyl flex duct, has a much higher roughness factor than sheet metal. That difference right there is usually represented in about 1 size difference of duct for round duct. So in other words, an 8-inch sheet metal duct, in order to get the same amount of airflow, you're going to need a 9-inch vinyl flex, okay, because of this roughness factor. So we default to flex duct. If you're doing a sheet metal design, you're going to want to make sure that when you go to the data tables and your ducts, oh, right here, you're going to make sure you sell these to sheet metal. Okay, they default to flex. Okay, I'm getting ahead of myself. So let's go back to friction rate. So we've got our available static pressure. The first thing it wants to know is component pressure losses. Okay, component pressure losses.
So these are just all sort of miscellaneous pressure drops that different various components sort of take away from your static pressure. You're starting with your bank account, your pressure bank account of 0.5, and these are things you have to buy right off the bat. One of the biggest things you have to buy is your DX coil, your evaporator coil, all right? And that's going to be, you have to look this up, but it's usually around 0.25, sometimes higher, sometimes lower. That's just a starting point. You'll go back and you'll actually start looking at real numbers and plugging those real numbers in, but this is a good starting point. Electric resistance heating coil we don't have. By the way, there's some suggested numbers in manual D for these. If you don't know an actual number, there are some suggested numbers. Hot water coil we don't have. Heat exchanger we don't have. Low efficiency filter we don't have. High or mid efficiency filter, that's kind of the thing these days. And a lot of people are designing to 0.1 or around 0.08. So you can pick a filter, those high MERV 13 filters that are now required in California. You're going to size your filter to provide this. So you're going to use this to pick a filter. Okay. Electronic filters, humidifiers, supply outlet, and return grill. Common numbers for these are 0.03 and 0.03. Again, that's a common number to use, and you can say, all right, I'm going to take that number and I'm going to go pick a supply register that gives me a pressure drop of 0.03. So it becomes a design tool. Okay. UV lights, we don't have branching damper or what's the other term? Bouncing dampers. Okay. You could put in a number there. All right. So we started with 0.5 and we're eating up 0.39, almost 80% of it. And so what we're left with, 0.5 minus 0.39, we're left with 0.11. That's called our ASP, our available static pressure. Okay. Now, step 4 is to calculate your total equivalent lengths. Remember that table I showed you with all the little fittings and stuff? So those are equivalent lengths, but you have to actually also account for the actual length of the duct. If that's 10 feet, you need to accommodate or count that 10 feet in the length. And the other thing too about flex duct is bends have equivalent lengths, and it's right around 10 or 15 feet, and you can look that up, okay? And you say, all right, so I've got, X feet of duct, I got a bend, I got a fitting, I got a fitting, got a fitting. The software, because of the way you've drawn this, will take a first attempt at calculating your total equivalent lengths. So you come up here, this little table. So friction rate is what we're looking at now. This is the friction rate worksheet. TEL is total equivalent length. So I'm going to click on that, and it brings up this other table. And here are our 5 supply runs, and they're going to bedroom 1, living room, kitchen, blah, blah, blah. Okay, so there's our 5 runs, and it's showing the current friction rate for each run, and it's showing the combined actual duct length of each run. Okay, any trunks and branches. We know that everyone has a register boot because of the way we drew that. Move this out of the way. So every run has a register boot. So that's 10 feet. You can edit these. If you're saying, no, it's a different kind of register boot that actually has 15, you can come in and edit these. This is just a first crack at it. The other thing it has is a start collar. A round duct attached to a supply plenum like this has an equivalent length of 35 feet for the air having to make that bend. And so there it is, 35 feet. So there's, each one has that. You can edit these, you can add to these. You can stretch it out. Let's see. One has a TY, but it's not showing up. TY. It should have calculated in TY, but there I see zeros in there. The TYs are 10 for the larger one, or for the straight run is 5 and
equal to 0.
Yeah, and then say 15 to okay. Don't stress over these. these equivalent lengths aren't super accurate to begin with. Even the tables that you're looking at, they were, done by University of Texas a long time ago in their lab somewhere. And don't stress over it, okay? Do your best, take some defensible numbers, just be able to say, yeah, I did this because I think this DY is one of these and it does this. Just think about it. Just be due diligence, go through, check it, okay? There's some others on the return side too. Okay, there's some stuff on the return side. And then it takes those equivalent lengths, and then you can look right here and it's calculating a friction rate for each individual run. And that's what will help develop a self-balancing system. You can use the worst case friction rate for the entire system and size all your ducts based on the worst case friction rate. But if you have a lot of variation in your ducts, it might not balance very well. So by using an individual friction rate for each run, it's more custom, if you will, okay? And so it will do that automatically unless you tell it otherwise, And the fact that we're using software to do all this math for us makes it easy to do that, okay? So I'm gonna go back to the friction rate table. So the total equivalent length, you can look at each one individually by clicking on each individual run and then the returns. So remember the manual D was suggesting between 0.06 and 0.18. I said, let's shoot for around 0.1. I'll go back to this because we can see them all. 0.08, 0.09, 0.08, 0.08, 0.07. So we're okay. We're looking okay. This might change later on, but this looks pretty good. We're in the ballpark. We're not below 0.06. It'll actually give you a little error message if you're below 0.06 or above 0.18. But we're close to 0.01 on some of these. Okay, I think we're okay. This is a good place to sort of work from, and then we'll fine tune it later on. All right, so we got our friction rate. Okay, so we got our friction rate for each ducts. Go back to the data table. We've got, go into our rooms. Here's our airflows, heating airflow, cooling airflows. We've got our totals. They're being distributed accordingly. Now, let's go look at the duct table. In the data tab, the duct table, and here's our run. Let me scoot it down where we can see the whole thing. If you click on this, it will highlight the duct. If you click on the duct, it will highlight it in the table. All right, so let's look at SB1. Supply branch 1 is serving bed 1. It has a friction rate of 0.08. It's currently a 12-inch diameter duct because that's what the default was when I first drew it. It's 11 feet long. Currently, there's a velocity of 135. The register is 12 by 6. This is just informational. This doesn't, you can change this, but it won't change any of your calculations. And it's attached to the base. It comes straight off. There is no trunk serving it, okay? Let's look at this one, bed 2. So this little run right here is called Supply Branch 4. It's serving bed 2. It has 84 CFM, friction rate's 0.08. It's only 3 feet long, and it is being served by a trunk called ST1, Supply Trunk 1. What is that? Well, here's this run. A trunk is a duct upstream that serves it. So that's going to be this duct up here. So you see this ST1. Look over here. Here's our trunks. There's ST1. Highlight it. There it is. So this one is actually serving 2. So if we go back to the table, there's the 2 that it's serving. Okay. So this trunk, the airflow in this trunk is 108. That should be the sum of these 2 branches that are being served by it. And if we look there, we got 84 plus 24 is 108. So those 2 branches are being served by that trunk, which means you add that airflow, and that's how much air is passing through that trunk. There's only one return. It's getting all the air. And remember, it's 646. Why is it 646? Because remember, some of the heating CFMs were higher than the cooling CFMs, so we're designing it to 646. That might be a little safe, okay, on the return, but don't stress about it. Don't stress about it, okay? All right, so we haven't auto-sized anything. So watch this column right here. We've got these, it's all 12 inches. I manually changed that return to 16 just to make it look a little more realistic as we were drawing the ducts. They all say 12 because that's what it defaulted to. Here's a magic little button over here that says auto size ducts. What it's going to do, it's going to look at this CFM, it's going to look at this friction rate, it's going to look at this type of duct, and it's going to size these ducts. So when you hit auto size duct, watch this column, watch these 12s will all change. 7, 8, 10, 6, 4. Also look at the drawing. They all changed. They're all to scale. So that little 4-inch duct, look how skinny it looks. It's a pathetic little duct going out there. It's only moving 24 CFM. Okay. This one here is a 6-inch duct going to that bedroom. We got a 7-inch duct going back here. And we've got a 8-inch duct going to the living room. And we got a big old 10-inch duct going to the kitchen. Why is that kitchen duct so much bigger than the living room duct? They're the same size room. It's exactly the same size room. It doesn't look like it from the angle we're at, but it is. Why do you think this room needs so much more air than this room? I'll tell you why. It's got a skylight facing west. It's got a west-facing window. It's got a door on the back. The living room has a window and a door, but they're facing south. There's also 1,200 BTUs of internal gain in this kitchen. So that percent of airflow is much higher than it is for the living room. Therefore, it's getting a much bigger duct. If you don't like running a 10-inch duct to a single register, split it in two. Let's do that. We'll just split it in two. So we'll come over here. It's going to get a little crowded over here. Go back to HVAC draw. So what I'm doing is I don't like a 10-inch duct going to a register. That's a pretty big duct going to a register. It's going to be a big funky looking register. So what I'm going to do, I'm going to split this into two. So I'm going to go to air registers. I'm going to put another one here. I'm going to move this one over. I'm going to go to flex ducts. I'm going to turn this fitting here into a TY. I'm going to attach it. Now, let's make it
Why didn't the friction rate change?
because the friction rate is based on available static pressure, all the pressure drops, and the total equivalent lengths. Those are what drive duct sizes. So the duct size changes because the friction rate is a certain number. So when the duct sizes change, the friction rate doesn't change. So those are sort of fixed based on other information, and they're being used to size the ducts. Okay, hopefully that makes sense. So I'm going to go back to data tab. I'm going to go back to
you press return to add the TY. Oh yeah. With the duct selected, whatever you have, you go to HVAC draw really quick.
Yep. So HVAC draw.
You'll have this little drop down here, and when you have one of these handles,
they can't see. So you see these orange handles here? You highlight those, you click on those, and when you hit enter, it's going to change that orange handle to whatever is selected over here where it says new fitting type. And it's right now it defaults to TY. Okay. I hope I don't mess things up too much here. I'm going to highlight this one. I'm going to pick something else. What should I pick? I'm going to pick, I like to pick splices. Okay. A splice is just two flex ducts connected end to end. So I'm going to turn this handle into a splice. And the nice thing about that, so now splice is selected. This is highlighted. I'm going to hit enter. And now you see that little splice there? That little splice, it put a splice there. The reason I like to do that is because now it adds two more handles. So now there's a handle there that I can move around, and there's a handle there that I can move around. It gives me more flexibility to, if I need to, move a duct around. Okay. So that's a splice collar. If you want to move that splice collar, you got to click on fittings, highlight that splice collar, and then you can do all this kind of stuff. You can change the angle of it. Got a lot of cool stuff you can do.
If you're feeling brave, you can do a Control Z.
Oh, yeah. So a lot of people like me, especially if you type a lot of documents, you sort of live and die by Control Z. You know, if you make a mistake, Control Z will undo it. That's a surprisingly difficult thing to program because in order to do Control Z, in order to go back one step, you have to remember those steps. And so you have to keep this running log of things that you did. So we do have Control Z in here, but it only works on a few things. One of the things it works on is placing something. And the other thing that it works on is if you just deleted something, it'll undo that delete. But if I were to move this and then hit Control Z, it won't move it back. We don't have that saved. If I were to delete something and hit Control Z, it will move it back. So what's happening? Oh, yep. So it took away that splice that I placed. Okay. All right. So what did we do? We split this duct. We didn't like that 10-inch duct going in here to one register, so we split it. So there's 2 registers blowing into the kitchen. We need to go back to data. We need to go back to the duct table, which we're at. And so we need to auto size. There we go. So now this is a 10, and it's splitting into 2/8. Back there, you can see that. And this one is 8-inch, and this one is 8-inch. They're served by, now there's another trunk. We had ST1 before, now there's ST2. ST2 is down here, and it's a 10. Because remember, we had a 10 going through there, and we split that 10 into 2/8. And so that 10 should stay there as the trunk, and it does. So it's a 10 splitting into 2/8. Okay. All right. We're getting close to quitting time. I promise not to run over like I did yesterday. So we basically have made the first pass through. Okay. By the way, if you don't like odd size ducts, some places, some people don't like odd size ducts like 5s, 7s, and 9s. Round up. Do not round down. Round up. The software will calculate odd size ducts up until 10, and then after 10, it's even sized ducts. That's how most well-stocked supply houses will have flex duct. Some parts of the country, some parts of California, in fact, they don't stock odd size ducts. They don't stock 5s, 7s, and 9s. So just round up to the next size. Okay. All right. The other thing I wanted to show you was, remember I said don't stress about total equivalent lengths and some of this stuff over here and your friction rate. So if we were off on our total equivalent lengths, if instead of 5 or 10 feet on the register boot, it should have been 15 feet, and it changes the friction rate here by a little bit, is that going to suddenly make a giant duct up here? And I just wanted to kind of give you guys a feel for how big of an impact friction rate has on duct size, okay? And the short answer is not that much, not that much. Going from 0.07 friction rate to 0.08, most of the time will not change the duct size, okay? So why stress about it? I don't know. It is an important number, and it's a number we need to calculate. It's a number we need to be able to defend, okay? See, the problem is most HVAC design in California, or in most of this country, I would assume, does not go to this level of detail. It's designed by trial and error, or designed by rule of thumb. If you go to ask them, what friction rate did you use on your ducts? They say, I don't know, what's a friction rate? Or what total equivalent length did you use for that fitting? And I don't know. The fact that you've come in and quantified these and done a defensible calculation, you are so far ahead of the average HVAC designer. you're in good shape. Okay. All right. So what was I talking about? We got that. Let me go back to data. Oh, I wanted to show if these friction rates change, how much do they have to change before these duct sizes start changing? And the best way to do that is I put together this very colorful table here. And
like a ductulator.
It's from a ductulator. A ductulator is another way to look at that. In fact, that's an excellent point. I should make that before I go on. If you've ever heard of a ductulator, it's a duct slide rule. The numbers on a duct slide rule, by the way, duct slide rules are for different kinds of ducts. Unless you have the nice one like the ACA one, it has all the different duct types. So it's got a wheel for flex duct, it's got a wheel for sheet metal. But a lot of the simple slide ones, the little in and out slide rule ones, you have to look on there and it'll say whether it's for sheet metal or flex duct. Okay, so you got your slide rule. You look at you find your friction rate. You slide the little friction rate arrow over until it lines up with your CFM, and then you look in another little window and it's going to tell you a duct size. Okay, when you have that ductulator, slide the window that has the duct size in it, slide that until the next size duct comes up and watch where it moves along the friction rate. Okay, that's another way to kind of get an idea for this. But what I've done is I've tabulated, there's no way you're going to be able to see these numbers, but I'll zoom in just so you can see. From this left-hand side, what we have is friction rates of 0.11, 0.10, 0.09, and 0.08, these 4 columns. And then the same thing over here. This table on the left is duct sizes 4, 5, 6, 7, 8, 9, and 10-inch ducts. This table to the right is from 10-inch up to 20, 10, 12, 14, 16, 18, and 20. This is available on our downloads page on our website, okay? And so what I want to show you here is from a friction rate of 0.11 through 0.1, 0.09, 0.08. So 0.11 down to 0.08. That's a pretty big drop in friction rate. 0.11 down to 0.08. Okay. What does it take to change the duct size? So now let me zoom in here. Oops. Zoom in a little bit more. So let's look at a very common sized duct. Let's look at an 8-inch duct. So this light blue color here is an 8, probably you can't see the top. Let's look at 6-inch ducts. So at a friction rate of 0.11, a 6-inch duct will handle up to about 76 CFM at a friction rate of 0.1. At 77 CFM, you've got to put a 7-inch duct, okay? If you look here from a range of friction rate, 0.11 to 0.08, from a CFM of 47 up to 61, there's this band across here. From this line here to this line here, this thickness right here is a range of CFM where the duct size does not change from a friction rate of 0.11 down to 0.08. So in other words, if you're at 60 CFM is your target, you're going to be a 6-inch duct no matter what your friction rate is up here, 0.11 down to 0.08. It's at 60 CFM, it's pretty close here. So it looks like if you went to 0.07, that might change. If you can imagine the next step down here might go below that. But if you're at, say, 50 CFM, you're going to be at a 6-inch duct no matter what. Okay. So there's these ranges here where it doesn't matter what your friction rate is. Anywhere between 0.08 to 0.11 is not going to change your duct size. So there's a lot of cushion, I guess is what I'm saying. Now, when you get into the bigger ducts, it's a little more exaggerated. But remember, on the bigger ducts, we're going in 2-inch increments. So we're going from 16 all the way up to 18. And from about 1,050 CFM all the way to about 1190 CFM. So 1050 to 1190 is this range right here. Your duct size doesn't change. An 8-inch duct will work from a friction rate of 0.11 all the way down to 0.08. Okay, so hopefully that kind of just illustrates, you know, we were talking about, I was saying don't stress on these little equivalent lengths. In order for the friction rate to change from 0.1 to 0.09, you've got to put in like 30 or 40 or 50 or 60 feet of equivalent length to change that. So the duct size is fairly immune to those little tiny changes, okay? Now, if you're right on the borderline, okay, it might make a difference. But remember, there's some cushion in the rest of the duct system, okay? There's a little bit of cushion in the rest of the duct system. And by that, I mean, you're always rounding up to the next size. So let's say our friction rate is 0.08, because that's what some of ours were. And let's say we had to get 500 CFM through a trunk. So 0.08, 500, we're right here, 500. That means we're going to use a 14-inch duct, okay? 14-inch duct. But that 14-inch duct will actually handle up to 600 CFM. So we have 100 CFM of cushion in that 14-inch duct because ducts only come in certain sizes. If they came in odd sizes, if there's a 13-inch duct, we might use a 13-inch duct. You know, if they came in tenths of inches, we might need to be more precise, but they don't. This is just the sizes that ducts come in, and the difference between a 12-inch duct and a 14-inch duct is huge. It's from about 400 all the way up to about 600. That's a 33% increase in capacity going from a 12-inch to a 14-inch duct. That's huge. Okay, so there's a lot of cushion. There's a lot of built-in cushions. Hopefully that just kind of gives you a little sort of comfort so that you don't stress about this stuff. All right. So guess what? We're basically done except to go back and fine-tune everything. So this duct size, oh, and let me show you a couple other features really quick. Let's go to Tracy Draw. If you want to see the duct sizes on here, down here there's these labels, so you can put dimensions, and it'll show the duct sizes, kind of floating above each duct. That's kind of cool. If you want to see the airflow coming out of each register, or going, I should say, going through each duct. I thought it was going to be in the registers. The airflow.
There's a little checkbox at the bottom.
Oh. Show CFM at registers. There we go. Let's do dimensions. Okay, there we go. That's good. So it's showing the duct size, 4-inch, and how much air is coming up the register. That's kind of overlapping a little bit. Okay, there's a couple other things. We did talk about velocity. For some people, velocity is an important consideration. In my experience, I've not found it to be that big of a deal because most of my design's in a dry climate. You do have to worry a little bit more about velocity in a more humid climate. Do keep that in mind. That's more of an advanced topic. All right, let's turn off all the decimal points on these. There's no reason to have 0.38 feet per minute, so we'll just clean that up a little bit. All right, so that's just a couple of little features. The other thing, if you want to create a plan that looks more like a traditional 2D plan, HVAC mechanical plan, one way to do that is to do it in 2D. So we go look at the top.
Someone's asking, sorry, where is it on your downloads page? I don't see it.
Oh, for that, shoot, I thought it was.
So which one?
That colorful chart.
Oh,
the friction rate chart. Shoot, I thought it was. I will put it up. I will promise to put it up later this evening. Shoot, I thought it was. I think it's called duct size versus friction rate. If you see something, maybe Google that Google duct size versus friction rate table and see if that comes up. But if it's not there, I'll make sure it gets up there tonight. I apologize. Actually, here, Connor, I'll just give it to Connor. He can post it on a Google Drive. Or I can do that. This guy here. So what do I do, Connor? Just drop him into a Google Drive.
Yep, and then you can just right click on after you drop it and do share link and post it into the chat.
We'll figure out how to open
Chrome, press the Windows key.
Share. Up it. Drop it.
It's not a fun.
Downloads. Sorry, everybody.
You can right click on that tab.
Downloads. It is friction rate.
Wait, you put it to a folder.
It's called Quick Model Flex Duct Isometry.
Right there. You click.
You do it. Put it into. You have access to that track.
You can literally just put it in the chat.
I don't have the chat open.
There we go.
All right, Connor's going to put it in the chat. And it's a link. It's called Quick Model Flex Duct Sizing Chart. Yeah. Thank you for letting us know. I apologize. I thought that was in there. I do want you guys to. I think it's a really useful illustration of friction rate and duct sizes. Okay, so I was talking about if you want to sort of create a plan to show somebody, what you do is you go view from top, 2D, and what it does, you look straight down and it flattens everything, so it looks more like a traditional duct drawing, if you will. I personally think it's very old-fashioned. What I would do if I was showing this to someone to install this. Let's say I designed this for my own house, and I said, "Here, install this." What I would do is I would take 3D screenshots, and I would look at it like this. I say, "Okay, here's what it looks like." Turn the rooms back on. Say, "Okay," and you can clean up the text and stuff like that. Like, you can drag these around too, can't you? Can you drag these?
Yeah, there's
TFP and HVAC draw.
I think you have to have it in Duct mode. Oh, on those it's on their handle. On the straight ones, you can drag them around.
Yeah. Okay. So you can move these numbers around. We'll make that a little easier to work with. But I think doing what we call isometrics in the plumbing world, isometric screenshots. Let me turn off those. That's part of it. You do isometric shots like that. So you look at it from different angles, take a shot, post that into a document, look at it from this side, take a shot, post it into a document, look at it from the front, look at it from the back. I think that, to me, for an installer up in an attic trying to run all these ducts, I think that's a lot easier to work with than, say, a traditional 2D drawing that's going to look something more like this. If you're lucky. Most of them don't even have the ducts, aren't even to scale. Some of the duct drawings I've seen from other software is just a squiggly line. And they're all the same dimension, they're all the same thickness. You can't do it so that it's to scale and stuff like that. I've also seen single line drawings. I've seen some really, really beautiful CAD drawings of a duct layout like this, but they were single line drawings. The ducts weren't even to scale. And flex duct curves. This is much more realistic of a flex duct situation, and gives them a much better visual representation of what the system is going to look like once it's actually installed. Okay. The other thing too, I didn't mention, if you look at it from the front, turn the rooms back on. Another reason that it might be worthwhile to draw a roof on top of this is it tells you how much room you have for your ducts. If you look here, and if you were to draw a line from this point down to here, if that was the roof line, it's actually a little bit higher than that. This duct might be hitting the roof. So you want to come back and say, all right, that's not in a good spot. Let's move this guy down, scooch him down, get him out of the way, like so. And now he's clearing the roof better. Okay, so that's a pretty cool little roof. All right, I've got a couple minutes left. I'm going to open up. I want to show you a couple of projects that are done. All right. So this is a two-story house that I did a while ago. And I'm going to turn off. So remember, in two-story houses, you got two floor plans. So there's a lower first floor. Remember over here in elevations, floor plan, elevations, we have this little guy here, and we had to add a floor. This is what happens when you do that. It creates like another floor level. It gives you another level to import a floor plan to. You've got to get those floor plans to line up, and then you have to put your rooms on there. And so I'm going to turn some of this stuff off so that it looks a little more normal. Not the rooms, the floor plan. We'll turn off the grid. Okay, and so now there's a two-story house. Let me darken the rooms a little bit. A little ghosty. There's a two-story house with a single unit. And you might be thinking, whoa, that's pretty ugly. Sorry, folks, that's reality. That is a 10 pounds of spaghetti in a 5-pound sack. And that's what a real flex duct system looks like up in an attic. They're not straight lines, okay? And if you get stuff like this, you may want to be careful not to draw it this way, because they might say, oh, that's how I'm supposed to install it, with this elbow in here. But, you know, put in the notes to install the ducts as straight as you can. This little guy here, that shouldn't be there. Let me fix that real quick. I'm just going to take that ugly bend out of there. So, looks a little better. Okay. But if you have to do that, you have to bend this around. That's an equivalent length that you can factor that in. Okay. Also, the other thing, how do you get to the first floor from an attic? Your furnace is in the attic. You've got to get down to the first floor. Let me turn off the second floor rooms. Look at that beast. The first floor has registers. How do you get down to those registers? This was one of the most challenging parts of HVAC design, with a two-story house with a furnace in the attic and getting the ducts down to the first floor.
Someone's asking how the chase function works.
Yes, chase function. So a chase is a vertical void in the walls that allows you to run a duct from the attic down to the first floor. So let me turn the rooms back on here real quick. I'm almost out of time. Okay. So the chase is, if I go into chase, is this, you see that highlighted blue duct right there? That's a chase. So it's actually a vertical duct, okay? But we call it a chase because it's inside of a chase. It's inside of a boxed out corner. If we look down at the floor plan here, you see down on the floor, they've boxed out this corner. So this boxed out corner, that's the actual chase itself, is the box. But we say we want to run a duct through that chase. And so we have this, it's basically like a fitting. Okay, let me see if I can place one here. If I just do Alt-click. See, I just placed one there. I'm going to line it up with that chase. Now I can attach a duct to the top and attach a duct to the bottom. We call that a chase. It's just a vertical duct, and it's treated like a fitting. Okay. And then when we get down to the floor joists are going to have some thickness to them. And lighten the room up. See if it's a little better. Okay, so basically what's happening is this duct is coming down until it hits the floor joist. It's running through the floor joist, and then it's dropping down into a dropped ceiling. A dropped ceiling is when you take the ceiling of a room, so you got this little bathroom here, and we've lowered that ceiling by 12 inches. And that's a feature. I'm sorry. That's a feature in the software called a drop ceiling, and it's in the rooms, and you can tell it how far to drop down a ceiling. But what this is like a fake ceiling. They'll lower the ceiling by 12 inches, they'll sheetrock it, and they'll run ducts through there so they can go perpendicular to the floor joists, because the floor joists are running front to back. So you really got to get good at reading structural plans. One of the mechanical engineering departments that I ran was actually owned by a big structural engineering firm. And that was cool because I could communicate directly with the engineer who was designing these floor joists and say, hey, I really, really would like the floor joist to go the other direction. And they say, well, we can make that happen in certain parts of the house. So they were able to accommodate some of the stuff for me. But most of the time you don't have that luxury, and you've got to deal with what they give you. If you don't design this house in advance, if you go out to the house without talking to the framer or anybody in advance and try to install ducts, you're gonna have a horrible, horrible time. They're not gonna give you room to run your ducts. So you need to do your duct design in advance, send it to them and say, please leave this floor joist bay open for me. Please don't run your plumbing through here, please. I mean, sometimes it's a struggling vein, but the whole point is design it first.
I missed a question from before. Doug was asking, what do you do to make sure your floor plan's aligned?
Oh, look at the rooms. So when you move your rooms around, when you place your room, I'm going to turn off the second floor. So you place your first floor rooms on the first floor, and then place your second floor rooms on the second floor, and then just make sure those corners line up.
We also have little markers on, if you go to floor plan mode.
Yeah, that's a good point too.
There's these like brown circles that you can click on. I'm not sure. Show the floor plans and hide the rooms. Or hide the, and then it's that brown circle there.
Yeah.
That'll be the same on both floors.
Yeah. So
just do a scale floor plan.
Yeah. One thing that will always line up between the first floor and second floor plans is going to be the stairs. So always use the stairs as a reference to line stuff up. Also, any like exterior corners. Go into 2D mode. That helps too. With the grid. And see if I move floor plan. I think I got something turned off. But this black dot here.
You need edit plan. The bottom one.
So you can move stuff around until you get them to line up. And so like use these scale marks. Like that.
And then the brown dot, you can show that you can drag that around.
Yeah. And this brown dot here will be the same on the first floor and second floor. It's like an alignment point which you can
scale. I'm sorry. Scales where you move all of like the rulers and stuff.
Yeah. Okay. So anyways, we've gone over time. Sorry about that. All right, everyone. Thank you so much for spending the time with us. We really appreciate it. I know there's even a 3-hour good movie is hard to sit through, and I appreciate you sitting through 2 straight 3-hour dramas with me talking nonstop. Hope you guys learned something. I'm sure Steve will be open to having more of these classes in the future. There's a lot of stuff. We'll get this class posted on our YouTube channel, or at least on our website where you can access it. There's other stuff. I hope you guys, whatever software you guys use, whether it's Elite or RightSoft or Quick Model, you're doing good. You're doing a good design. You're way ahead of the average contractor. And we encourage you to do that. There's a lot of classes. There's a lot of good stuff online. And my goal, my personal goal is to make HVAC design standard practice for everybody. And I hope we do that by having a simpler software, a 3D software, but also by introducing other people to it, like energy consultants, architects, get other people out there, HVAC contractors. A lot of them aren't even computer savvy. So get other people that they can go to and have them do a quick design for them, cheaply, simply, so that it becomes much more standard practice. So that's what I'm hoping to do. And if it takes teaching everybody individually, then